All right, these notes are going to be on Euler's method, and it is spelled totally differently than it sounds. I don't remember the mathematician's first name, but his last name is Euler. So Euler's method, not Euler's method. People will laugh at you. Euler's method. And what Euler's method is it's a numerical approach to finding a particular solution of a differential equation. So yesterday we were looking at slope fields, and with slope fields, those were a graphical approach that showed all of the solutions for a differential equation. And then once we were looking at those slope fields, we could pick an initial value and trace it, and that would have been one particular solution. So what Euler's method does is it's a numerical approach instead. We're going to plug some numbers into things, and it's a numerical approach not to finding the whole family of solutions, but to finding a specific solution for that differential equation. It uses parts of tangent lines to approximate the solution. So this is similar to, but not the exact same thing as what we did before. I believe it was in the applications of derivatives unit, where we did what we called linear approximation or tangent line approximation. We said we don't have the original function, so we can't plug a number into the curve to evaluate it. But if we have a point on the curve and we have the slope of a point on the curve, then we could use the tangent line. And any point that was close to that point on the curve, we could plug it into the tangent line, and we'd know that we didn't have the exact evaluation, but we had something close. This is a similar idea where we're going to have a differential equation we can work with. We're not going to know the exact solution to the differential equation because it's in terms of x and y, and maybe solving for the original function is something that's a little outside of what we're capable of at this level of mathematics. But Euler's method allows us to find a curve that's going to approximate that solution. So while we can't get perfect answers, we're going to get pretty close. All right, so there are three pieces of given information that you will have when you're using Euler's method. You'll be given an initial point, which I'm going to call x sub 0, y sub 0. You're given the differential equation, which I'm going to say is y prime equals f of x, y. So remember, when we looked at differential equations, it was a function of x and y, not necessarily just a function of x. We're going to go ahead and remember that this differential equation is also where we get our slopes from. And then they're going to give us our step size, and they write it as h or delta x typically. And your step size is kind of like the idea of saying, if you were to draw a slope field, how populated your slope field is. So are you finding the slopes at all the whole numbers? Are you finding slopes at all the halves, all the fourths, all the sixths, all the eighths? As you can imagine, when we had those slope fields that were a lot more like populated, I guess, that had a lot more slopes in them, it was easier to start with that initial value and then trace what we thought the equation looked like. So when the step size is smaller, we can get a more accurate picture. When the step size is bigger, it's easier to do the problem, but it might be a little bit harder to figure out what our curve is with as much accuracy. All right, so what I'm going to lead you through next is I'm going to show you kind of where Euler's method comes from so that we can make a little bit of sense of it. And then after that, I'm going to show you the way that we're going to go about doing it. All right, so Euler's method is based off of a recursive function And we don't deal with recursive functions a lot when we're dealing with algebra. The one place you might have seen it before is in talking about sequences and series. So we always deal with explicit functions where you can, to find whatever point, you just plug a number in, that gives you the exact point. A recursive function says that to get an answer, you have to do something based on the previous answer. And so it's kind of like a chain of events. One answer leads to the next, leads to the next, leads to the next, and that's the only way to get through to a bunch of different terms. And so you would have seen this in arithmetic and geometric sequences, typically with recursive formulas, but that's what it's based on. So I'm gonna go ahead and show you an XY table. And this is not exactly how we're going to do Euler's method. Again, this is just me explaining where it comes from. So we start off with those initial values, x sub 0 and y sub 0. And then what we do to find the first x value is we take the initial x value and we add h to it, which we said was the step size or the change in x. So if we're finding a more accurate representation of the curve, then we would have a smaller step size. Maybe we're changing our x value by 0.1, so that would be fairly accurate. Or maybe we don't want to do as many of these, so we're changing it by 0.5, or we're changing it by a whole number. It depends on the problem. And then the y, the first y term, remember what we're looking for here is those little slopes, right, that we have on a slope field, and those are straight lines. So for the y coordinate, we know that y coordinates of straight lines always come from the formula y equals mx plus b. And so the y value comes from f of x sub 0, y sub 0, because that's our slope, right? That's our differential equation. It's where our slope comes from, times that change in x value plus the initial y value. So we have mx plus b, right? Then our second x value is our first x value plus the change in x. Our second y value is the slope as calculated by now the x1, y1 times that change in x plus y sub 1. So each term we get after that is based on the one before it. So when we go through and we do Euler's method, it means we're going to be filling out a table and walking ourselves through a process, and then eventually we're going to get to an answer that we can work with. All right. So basically from this, we can write a little formula from this. I'm not going to ask you to show me this process again or manipulate this process right here. It's basically, we're going to look at a table and we're going to memorize how to use it. We're going to do it the same way every time. But this isn't a bad thing to have in your notes, just if you ever need to look back. Or let's say you're taking a college class and they go over it again and you're a little bit confused. These notes could be good. Okay, so the way the new x coordinate is found is you take the old x coordinate and you add the change in x to it. The way you find the new y coordinate is you take the slope as determined by the differential equation and you multiply that by the change in the x value and you add the old y value. All right, so one thing we're going to go ahead and write in our notes is that the smaller the step size, the better the approximation. Smaller line segments make a smoother curve. All right, so I'm going to go ahead and draw just kind of an example of this so you guys can see it. So let's say that this right here is the curve that we're trying to make. And let's say that I broke it up so that these are the width of my line segments. So what we would say is like, this is my initial value right here. And so I'm starting with that, and the slope right there is like this. Then my second value is going to be this x value, and my slope right here looks like this. So you can see the further I'm going with my line segments, the further away from the curve that I'm getting. Now it's a reasonable approximation of that curve. It's still kind of following it, but you can see it's getting less and less accurate as we go. If we think about the same curve, and we do line segments that are a lot closer together, then we can start with that initial value and follow that slope. And then we have this one, and we're following this slope, this one following the slope, this one following the slope. And you can see that since my segments are so much narrower, that my slope is a lot more accurate. So this is similar to the idea that we kind of talked about when we learned about Riemann sums, is that this is a tedious process, just like Riemann sums was. So when we were finding the areas of rectangles, we'd say, yes, the more rectangles you have, the more accurate your answer is, but it's also really frustrating to try to find 50 rectangles. So sometimes you sacrifice accuracy just for convenience, and that's going to be the same sort of thing with Euler's method, is sometimes we won't do as many narrow pieces just because it's more obnoxious. All right, so we're going to go through 2 example problems using Euler's, so that we know that we can work with the process. So the example says, use Euler's method to approximate the solution for y prime equals x minus y through 0, 1, with a step of 0.1 and 4 steps. Now the same problem, you could have approximated a solution for the differential equation x minus y through the point 0, by drawing a slope field and finding the point 0, and kind of tracing that curve. That would be one way to approximate the solution. Euler's method, again, as I said, is the other approach to do it numerically instead of graphically with a picture. So whenever we do this, especially when you're looking at the AP exam, they're going to specify use Euler's method or use a slope field, because they're 2 different approaches to accomplish the same thing. All right. So here is the table that we're going to make. You can call it, I call it x old, y old. I've seen some people just call it xy. And then we're going to have our step size. You can label this as x, delta x, or h, whichever you prefer. Then we have our slope, which is our differential equation. So dy dx equals x minus y. Yes, I switched it. No, I don't know why I did that. And then we have what I write here is I've got m delta x plus y old. Reminds me of y equals mx plus b. And then we have y new. There are simplified forms of this table where they really condense it down, but what I found is that it's hard for me to remember all the pieces because you have to do more in your head that way. This version of the table helps me to just kind of lay it all out there and be able to follow through each step of the process. All right, so if you want to simplify this table after you've done it several times, you're welcome to. I don't necessarily recommend it. So we're going to start with the point 0, 1. I know that my delta x is 0.1, and so my next x is going to be 0.1, then 0.2, then 0.3, then 0.4, and I knew to go to 0.4 because it said to do 4 steps. That was terrible. Let me make it go all the way down. There we go. Okay, so my delta x is going to be the same every time. That's never going to change. The reason I drew kind of squigglies down here is that when we're finding the solution, we're looking for the point at the very end. So this right here is going to give us a point at the very end, and that's going to be our solution, and we're not going to go any further than that. All right, so 0, 1, if I'm looking for my slope, I have to do x minus y, which is 0 minus 1 equals -1. Then I do that slope times the change in x plus the old y value. So I've got -0.1 plus 1, which is just 0.9. All right, so my new y value is 0.9. Now I'm going to go ahead and do 0.1 minus 0.9 equals -0.8. I have -0.8 times 0.1 plus 0.9. So this is my slope times my delta x adding to my old y value. And if you plug this in a calculator, you get that that result is 0.82. So now my old y value is 0.82. I'm going to do x minus y, so 0.2 minus 0.82 is -0.62. So I've got -0.62 times 0.1, so the slope times 0.1 plus the old y value, which was 0.82. And if I plug that into my calculator, I get 0.758. So now that's my old y value. So I've got x minus y equals -0.458. And so I've got my slope times 0.1 plus my old y value, and this gives me 0.7122. All right, so they're saying we're using Euler's method to approximate a point. And the point, we're doing it based off of the curve that would have gone through 0, 1 on that slope field. And they're asking us to approximate what happens if you take the function and you plug in 0.4. Well, if I take the function and plug into 0.4, I'm going to get approximately 0.7122. Somewhere around there, that's my approximation of that specific solution on that slope field based on the differential equation. All right, we're going to do another example. We're going to find y of 1.6 when dy dx equals x over y through the point 1, 1, and the h value is 0.2. All right, so I'm going to make my table. X old, y old. I'm going to go ahead and figure out how big my table should be. So I have the point 1, 1. I have an h value of 0.2, so I've got 1.2, 1.4. I'm going to 1.6. All right, so I know that's where I'm going to stop. I have my delta x. I have dy dx equals x divided by y. I have m times delta x plus y old. And I have y new. All right, so my delta x each time was 0.2. I always do this because I found that if I don't, I keep filling out the table and I go too far. All right, so dy dx is x divided by y, which is 1 divided by 1, and that just equals 1. So I have my slope times delta x plus my old y value. So that's 0.2 plus 1, which is 1.2. So 1.2 is my new y value. All right, now I have x divided by y still equals 1. My slope times 0.2 plus 1.2. That's going to be 1.4. So my y value is 1.4. X divided by y equals 1. My slope times my change in x plus my old y value equals my new y value. And here's my answer right in here. So I know that if I take the function that is represented by this specific solution of that differential equation, if I take that specific function and I evaluate it at 1.6, I get approximately 1.6. It's not the exact answer, but it's pretty close to what it should have been. So what we're going to do is we're going to just work with this tedious process of filling out this table over and over. I wish that I could say these problems aren't on the AP exam, but I've seen a lot of sample problems that use this table, and so it's going to be something we're going to try to have to memorize and retain so that we can remember it later.